11.3 Perimeter and area of similar figures. Go ahead and draw what you see. Two rectangles, one smaller with a side length of 2, other 3, and then the other rectangle is 2t, 3t. Let's find the ratio of the perimeters. Notice these are rectangles, which means this is 2 and this is 3. This rectangle over here is 3t and 2t. If I were going to find the ratio of the perimeter for over this other one, the small to the big, I would say, well, 2 plus 2 plus 3 plus 3 divided by 2t plus 2t plus 3t plus 3t. Let's go ahead and simplify this and see if we notice something about it. Notice this is 4 plus 6, which is 10, and that's over 10t. Well, when I reduce this, this becomes 1 over t. Interesting. Let's go ahead and do the ratio of the areas. Now the area is just 2 times 3 divided by 2t times 3t. This reduces to 6 over 6t squared, which reduces to 1 over t squared. What I want you to notice here is that these ratios are in fact different. You can think of this as being in the first quadrant, or excuse me, the first dimension with a power of 1, because we're talking about side lengths. This has a power of 2, which means the dimension's in the second, it's the second dimension. So we have 1 over t squared. This is just a beginning thought to illustrate the main concept. Go ahead and draw these two figures. We're going to use these two figures to establish a basic concept between finding the ratios of areas and perimeters of similar figures. All right, the side length of polygon 1 to the side length of polygon 2, this would be a over b. But the ratio of the areas is a squared divided by b squared. Now, what I'm about to say is actually what will blow many people away, and that's that the perimeter of polygon 1 over perimeter of polygon 2 is equal to the same ratio as the side lengths, because this is in the first dimension. First dimension is side lengths. First dimension. So the perimeter is also talking about side lengths, whereas this is talking about the area. Extending this concept, we can do volumes, but we're not going to do it here. I'm just illustrating it here. We're not going to do it later in this section. I'm just illustrating it here. Sorry about that, Bell. So let me illustrate that further here. Now, notice this becomes a side length divided by the side length is the same as the perimeter, or the difference in the perimeter. Notice the side length from this to this is 2 divided by, if I'm dealing just side lengths, 2 divided by 2t, which is 1 over t. We got the same thing from the perimeters here. All right, let's start solving some problems. If you're told that these two triangles are similar, that means their sides are proportional. Find the indicated ratio of red to blue. Well, red to blue of the perimeters is 8 divided by 12 because it's the same as the side lengths as I just showed you. Notice this reduces to 2 divided by 3. The ratio of red to blue of the areas, on the other hand, is those squared, 2 squared over 3 squared, because we are now in the second dimension, 4 divided by 9. Go ahead and draw these two problems down. Write these things down in your notes. All right, go ahead and draw this figure. You don't have to have it as thorough. At least draw the two rectangles, unless it tells you they're squares, but at least, oh, it does tell you that. No, it doesn't. Sorry. Stuart is installing the same carpet in a bedroom and a den. The floors of the rooms are similar. Floors of the rooms are similar. That means their sides are proportional. The carpet for the bedroom cost 117. Carpet is sold by the square foot. How much does it cost in the den? I would like for you to solve this problem on your own, and we will talk about it next class. Refer back to the textbook because it's in there. All right, guided practice. Pause the video, see if you can get the same thing that I do on this one. And this one I'm actually going to do in the video. All right, I got 36 feet squared. I'll talk through the process just for a second in case you didn't quite get that. Notice the ratio of the perimeters is this, which reduces to this. And notice if you square the ratios of the perimeters, you get the areas, and that becomes this. Then I take this and set it up with a proportion with 64 over x, because 64 goes with the 16, which goes with the 4 square, which goes with the 4. I just cross multiply this and solve for the other area. Remembering that area is in the second dimension. All right, Large rectangle baking pan is 15 inches long and 10 inches wide. A smaller pan is similar to the larger pan. The area of the smaller pan is 96 square inches. Find the width of the smaller pan. I would like for you to try this problem on your own. Come back next class with it done. It is in your textbook if you need to refer to it. All right, regular polygons are always similar to each other. I would like to illustrate this in Sketchpad, and I decided to go ahead and build it in Sketchpad with you. So give me a second while I pull it up. Let's talk about polygons for a second. Notice if I were going to build a hexagon, I would need to rotate this point around this point 6 even times within 360. So if I rotate this, that's obviously 60, but you can also type it this way, 360 divided by 6, which is 60 degrees. So I'm going to rotate this 6 times, and we're done with that. Let me go ahead and hide this, and let me create some segments. Now notice this hexagon is representing all hexagons, and all hexagons are always similar to each other. That means that this hexagon is similar to this one if I make it bigger. Hexagons are always similar to each other. So I'm going to move this over. I would like for you to draw these two in your notes, and we're going to mark them up together. Actually, let's make this one smaller. So the hexagons are always similar as long as they're regular. Pentagons are always similar, and so forth, because remember that similar means that all the angles are congruent, and it's regular, which means all the angles have to be congruent. And all the sides are congruent. Well, in one figure, they're congruent within themselves, but their angles are congruent, which means that they are also similar. I'm going to go ahead and avoid doing the pentagons because I think you got the basic idea. With that, we can answer questions like this. Like the floor of a gazebo is shown regular octagon. Each side of the floor is 8 feet. 8. Notice I went ahead and drew an octagon. Draw this in your notes because you're going to need it. And then it says the area is 309 square feet.
Hello?
1 second. Sorry about that interruption. We have a side length of 8 and an area of 309. Again, I would like for you to try this problem out on your own. Square feet. Try this problem out on your own. Check your textbook if you're still confused about it, and we'll go over it next class if you're still confused. All right, go ahead and pause the video. I'm going to try these two problems, write them out, see if you get the same thing I do. All right, I'll just talk this one out with you. Notice we have two decagons that I went ahead and put in here. We have a side length ratio of 20, or excuse me, area ratio of 20 over 36. If I were going to go down a dimension to side lengths, it'd be root 20 over 36. Remembering that root 20 is root 4 times 5. Root 4 is 2. Root 5 is just root 5. Root 36 is 6. Over here we have the ratio of the perimeter is 66 over 110. Noting if we turn this into the ratio of the areas, I have a therefore sign. That becomes 66 over 110. I just simply typed this in the calculator and said math frac enter, but you could do this with some tedious arithmetic and get 9 over 25. I took that and set up a ratio with my areas with 700. So I got 700 because it's 20 times 35 for the area of the second rectangle. I just cross multiplied this now that I have my ratio for the areas, and I solved. That's it for the notes.